Hi everyone, the purpose of this video is to review Ohm's law with you, not only definitions, but also take you through some practice problems and learn how to calculate using Ohm's law as well. So by now you should have worked through the lab. You should have submitted that and seen the key for the lab. And the purpose of this notes is just to supplement that. So you should have seen Ohm's law through the graph that you created during the Ohm's law lab. Ohm's law essentially is what it says is that resistance is equal to the change in voltage divided by the current. What you will most commonly see Ohm's law written as is the following. Voltage is equal to the current multiplied by the resistance, or V is equal to IR. I would box that equation up, put it someplace safe. That is the most common form of that equation that you will see. That is the form of the equation that I will start with when I work through this problem set here. So just as a quick little review, because you've seen these three variables before, but just to review them, resistance, which we use the variable R to abbreviate resistance, is still measured in ohms. And this symbol might be a little tricky to draw, but the symbol for ohms is that. Current, not as intuitive, is represented by the variable capital I, is still measured in amps, which we abbreviate as A, and voltage, V, is measured in volts, abbreviated by capital V. So it's really important, if you can't keep these variables straight, flashcards are a great resource to use, but you need to know resistance is R, current is I, and voltage is V. So voltage is equal to current multiplied by resistance. That is Ohm's law. Not only is it important to know what Ohm's law is, but it's also important to know the relationship between I and R. To look at this, you should have seen this relationship in the Ohm's law lab. We're going to look at it again. So when I go to my PhET app, this is actually still up from when I worked through the lab. I have my voltmeter there, and I also have my ammeter here, so it's measuring current and voltage. Now, I am not going to change the voltage on my battery, so I'm going to keep my battery the same. The reason why is because if we go back to this note set here, it says, what is the relationship between I and R? What this means is that the variable that's staying constant is V. So V is constant. That's important for us to know. What that means is that our power supply is staying the same. This would be equivalent to using the same amount of battery, and that's what we're doing here in the lab. So I'm going to take this voltmeter and put it back there so we can see current, and I'm going to highlight my resistor here. So currently, pun intended, currently I have a current that's running through the circuit with a value of 1 amp. And the resistance on my resistor is 15 ohms. What we're going to see happen, or what we're going to try and see, is the relationship between current and resistance when I increase the resistance on my resistor here. So I currently have a resistance of 15 ohms. If I start to increase that, I want you to watch what happens to the current. So I'm increasing my resistance. This would be like changing the appliance that you're plugging into an outlet, and the outlet that you're plugging in has more resistance than the previous outlet. And so what you can see is as my resistance goes up, whatever appliance I'm plugging in, that's what the resistor is symbolizing, as my resistance goes up, my current is going down. The way you can literally think about this is the higher the resistance, the more difficult it is for that current to pass through. So mathematically, we can say that that is an inverse relationship between resistance and current. The higher, and I can make this as high as it goes, right? The higher that resistance, the lower the current. And you can physically see, if you look at the blue circles, what are representing electrons there, blue circles with the minus sign in between them, Those are physically representing the electrons. And as the resistance is so high, it is preventing them from going through that circuit as fast, right? It's lowering the current in that circuit. So putting this into words, as resistance increases, current decreases. Right? And as we said, this is an inverse relationship between the two. Now, remember that relationship is strictly talking about when voltage is held constant. If we're not holding voltage constant, the relationships are going to change and we're talking about something else. But when that power supply stays the same, if you increase the resistance, what that's going to do is lower the amount of current that is allowed to flow through that circuit. All right, so moving on. Now we're going to go through 4 different practice problems on how to use that mathematical relationship. While I go through this, I want you to take note of how I'm setting up the problem, how I'm listing my givens initially, how I'm reading through it. That's important in order for you to successfully solve these problems. And I want you to model that as best as possible so that you're most successful when you're solving this. At any point in time, feel free to pause. For example, I have all of my answers already solved, so I'm not going to physically punch them into my calculator right now, but you should pause this however you need, fast forward if you've already looked through it. But I encourage you to pause this, practice punching in your calculator, make sure you're getting the same answer that I am. So for this first problem, it says, a car battery pushes charge through the headlight circuit with a resistance of 10 ohms. I'm going to highlight that because that's important information. If the circuit uses 1.18 amps, and again, amps is telling me the amount of current, then how many volts must the car battery be operating with? So first thing I'm going to do on the side here is list my givens. So the first thing that they gave to me in the problem was the resistance. So the resistance in this problem is 10 ohms. Second thing that they gave me in this problem was the current, which is abbreviated as I. Don't write A there. I know that the unit for current is amps, but the variable for current is I. So current is equal to 1.18 amps. And just to remind myself, voltage is what I'm trying to solve for, so I'm going to put a question mark there. So we start off with Ohm's law. V is equal to IR. In this problem, I'm trying to solve for voltage. That equation is already solved for voltage, so I do not need to use any algebra here to rearrange that equation to solve for a different variable. I can simply plug in what I have. My units are all in the units that I need to have. Resistance needs to be in ohms, current needs to be in amps, and voltage needs to be in volts. I don't need to convert anything. I simply need to plug in and multiply. So V is equal to, my current is 1.18 amps. My resistance is 10 ohms. And this is a good time if you want to pause, check to make sure you know how to multiply 10 by 1.18 when you punch that in, or for those of you that can simply hopefully do that, 1.18 multiplied by 10 is 11.8, and the unit on that would be volts. Very simple plug and chug type of problem using Ohm's law. Next question says, an old school Sony Walkman uses 2 standard 1.5 volt batteries. How much resistance is in the circuit if it draws a current of 1.13 times 10 to the negative second amps? So same thing as before, I'm going to write out what I'm given. So in terms of voltage, this problem says that I'm using 2 1.5 volt batteries. Now, if I'm using 2 1.5 volt batteries, the total voltage that I'm going to be supplying to that Walkman, for those of you who don't know what a Walkman is, this is what was invented before iPods, before CD players. Now everybody uses their phone and uses Spotify, but if there's 2 1.5 volt batteries, that means the total power supply would be 1.5 times 2, which is 3 volts. If I keep reading on in the problem, it says how much resistance is in the circuit if it draws a current. So current is represented by I. Our current in this problem is 1.3 times 10 to the negative second amps. The question then is asking me to solve for the resistance, so I'm going to put that question mark there. Starting with the same equation as before, Ohm's law, V is equal to IR. This time, the variable that I'm trying to solve for is R. This equation is not solved for R, it's solved for V. So I do require a step prior to solving. So I need to get R by itself. Currently, current and resistance, I and R, are being multiplied by each other. In order to undo that, right, or the inverse of multiplication is division. So the way I'm going to get R by itself is by dividing out that current, and whatever I do to one side, I need to do the other side. So my left side will become V divided by I, or voltage divided by current, and my right side will simplify to resistance, which is good because that's what I want to solve for. It simplifies to resistance because when you have I divided by I, that's just simplified to 1. 1 times R is just R. So now that I have an equation that is solved for the variable that I need to find, I just plug in, since everything's in the units that I need. So resistance is equal to voltage divided by current. My voltage is 3 volts. I'm going to divide that by my 1.3 times 10 to the negative second amps. It's important that when you're plugging this into your calculator, so this would be a good time to pause after I explain this. It's important that when you're plugging this into your calculator, especially if you're plugging that denominator in scientific notation, you need to put parentheses around this denominator. Otherwise, your calculator may not perform the operation that you want it to. So make sure you put parentheses in that denominator so that you're calculating this correctly. So if you want to go ahead and pause, try it out first, and then come back. The answer that you should get for this problem when you take 3 volts and divide it by 1.3 times 10 to the negative second amps should be 230.8. Now, you're calculating a resistance, so this needs to have units of ohms, and that is your final answer for this problem. Okay, so 2 problems. First one required no algebra first to rearrange. Second one, we're solving for resistance. In the next 2 problems, we're going to solve for the other variable that we still haven't found, which was current. So continuing on with this practice, this part says what current flows through a hairdryer plugged into a 110 volt circuit if it has a resistance of 25 ohms. So this is the third type of problem that we can assess you on. So first thing that's given to me in the problem is 110 volts. That's a voltage. So V is equal to 110 volts. The next thing that's given to me in this problem is resistance. So resistance is R is equal to 25 ohms. And in this problem, I'm trying to figure out how much current is going to run through that circuit if the power supply is 110 volts and the resistance of that hairdryer is 25 ohms. Ohm's law, V is equal to IR. This time, I'm solving for I. So in our previous problem, we tried to solve for R, so we divided by the other variable. We're trying to solve for I this time, so I'm going to divide out R so that these R's cancel. Whatever I do to the right, I must do to the left. So my left-hand side of that equation will become voltage divided by resistance, and that will be equal to my current. And so if I look at my variables, my voltage is in volts, my resistance is in ohms. All I do now is I plug in and I solve. So my voltage is 110 volts. I divide that by resistance, which is 25 ohms. So go ahead and try that in your calculator. When you do take 110 volts and divide by 25 ohms, the current that you will get is 4.4 amps. That's the unit for current. That should be our final answer for this problem. Now, thinking practically about what this actually means, B is asking you almost an extension to this problem. It says, if the same hairdryer were used in London, where the power grid operates at 220 volts, then what current would the dryer draw? Now, it is the same appliance, and that's important because what that tells you is that if that hairdryer had 25 ohms of resistance in part A, it will also have 25 ohms of resistance in part B. It is the same appliance. So I can take that resistance and use that same value for this problem. The variable that does change in this problem is the voltage, as it says right here. The grid operates at 220 volts, right? That's a different voltage than that was given to us in part A. So V is equal to 220 in this problem. They did not have to give you the resistance because it can be assumed that because it's the same hairdryer, it has the same amount of resistance. That's an important key concept for us to get. Now, in this problem, we're solving for the same variable. So question mark on current once again. But if we're thinking about this, right, so we have an increase in voltage, resistance is staying the same. You can make a prediction before you even solve this problem. So what I want you to do right now is I want you to pause and I want you to make a prediction. What's going to happen to current? Is it going to go up or is it going to go down? Now, whatever prediction you made, hopefully you used Ohm's law to make that prediction. We have an equation that says V is equal to IR. Previously, we talked about the relationship between I and R when V was staying constant. If I goes up, R goes down. If R goes up, I goes down. But this time in the problem, voltage is not remaining constant. Voltage is actually increasing. So what would be most helpful for me is to rearrange this equation to solve for whatever variable is staying constant so I can make that prediction. I can rearrange this and solve for R. R would be equal to V over I. Now in this problem, R is staying constant because it's the same appliance. It's the same resistance, which means the fraction V over I also has to stay constant. If it doesn't, then you're going to have a different resistance, which can't be the case. So if we think about this, right, if voltage is increasing, therefore doubling, right, so that's essentially what happened. Voltage doubled. Current also has to double in order to keep that fraction remaining the same value. So that's the prediction we have going in. Let's actually solve this problem and see if our prediction is correct. Prediction is if voltage doubles when resistance remains constant, current should also double so that that resistance stays the same. So in this problem, we're solving for current. V is equal to IR. We already rearranged this equation to solve for current in the last problem. We rearranged it to say current is equal to V over R. Our new V in this problem is 220 volts. We divide that by our same resistance of 25 ohms. And when you take 220 volts and divide it by 25 ohms, and you punch that in your calculator, you will find that the current is 8.8 amps, exactly doubled the current from the previous problem, proving that our prediction was correct. If voltage doubles, so does current in order to remain, have our resistance remain the same. So that, ladies and gents, is 4 practice problems that kind of hopefully help you feel more comfortable using Ohm's law. You have this problem here, the first one. You're solving for voltage where no rearrangement needed. Second problem here, we're solving for resistance, rearranging Ohm's law accordingly. And these 2 problems, we're both solving for current, just a little variation of the 2. Very last thing I wanted to talk about with you is electric shock. So the human body, almost like an appliance, also has a resistance, and our resistance is through our skin. Typically, when our skin is dry, that resistance is 500,000 ohms, a large amount than the previous problems that we've been using. But when your body is soaked with salt water, so like when you sweat, perspiration, the resistance actually decreases of your body to, at times, 100 ohms. Now, for those of you who remember chemistry, this should intuitively make sense. At some point throughout chemistry, you might have used a conductivity tester. And when you take salt water, which salt is a substance that when in solution, it conducts electricity. That, because it conducts electricity, it helps your body allow more current to almost run through it. So that's why the resistance decreases, because that salt water is actually helping those electrons move through your skin. Now, how does this affect the current when you're working with a 120 volt outlet? So remember, V is equal to IR. And if V remains the same, right, this is a 120 volt outlet. We're not changing the amount of power supply. If your body has sweat on it, right, that decreases the resistance. So I'm going to put a down arrow for resistance right here. What that means is you've now made it easier for those electrons to travel through your skin. Current will go up, and that's when, you feel that electric shock. That's why when you sweat or anytime there's water associated with it, there is that danger, that potential for that electric shock, because you're decreasing the resistance of those electrons through your skin. Again, proving the relationship between current and resistance and using Ohm's law, a nice little application of everything we've been talking about. So that sums up the notes for Ohm's law. The next thing that follows is a worksheet that practices similar calculations with Ohm's law. Instructions are to complete that worksheet next. And then once you make a submission for that worksheet, the key will be available for you as well. Always remember that during this module, you have the option to post in the discussion boards if you have a question, and also pay close attention to the office hours for this module. They are posted in the task list underneath module 2.